what does nitrogen become when the sun comes up? Daytrogen. Welcome to Space According to Skylar, and today we are going to talk about what is going to happen to our sun. And in order to do that, we need to talk about what is currently happening to our sun and what has already happened to the sun. So really, this is a video on the stellar life cycle. So we start at the beginning. I've heard it's a very good place to start. And our sun, like all stars, form in a nebula that looks kind of like this. It is essentially a giant region of gas in space. Now, in these big gaseous nebulas, there are regions that are higher density than other regions, and those high density regions can start to gravitationally collapse in on themselves. So, you have a big cloud of gas that is collapsing in on itself. What's causing this collapse is, of course, gravity. That's our primary attractive force in the universe. So gravity is pulling all of this gas together. And as this gas gets into a smaller and smaller region, it starts to heat up. You see, when you put gas molecules in a smaller and smaller space, they start to move around faster, kind of like a cat. The more you try to trap it, the crazier it gets. Everyone say hi to Atlas. So as this gas collapses in on itself, the molecules start moving faster, which means it starts to heat up, which means it starts to exert a pressure on the gas that is trying to collapse. So you have this external pressure and then the inward force of gravity, and eventually these two things will balance out. When gravity and pressure are in balance, we call this hydrostatic equilibrium. And when your collapsing cloud of gas gets to hydrostatic equilibrium, it becomes a star. Well, not quite. In order to be a star, you have to be able to do one simple thing: hydrogen fusion. What that means is you have to have enough energy in your core to take hydrogen atoms, combine them, and turn them into helium. It is through this atomic fusion that stars produce energy. Every single star we see in our sky emits light because it is fusing smaller elements into bigger ones. When a star is doing hydrogen fusion, turning hydrogen into helium, we say that it is on the main sequence. Our sun right now is a main sequence star. It is turning hydrogen into helium. It has been doing that for a little bit over 4.5 billion years, and it will probably do that for another 5 billion years. But eventually, our sun is going to run out of hydrogen. Our sun is not infinitely large. There's a finite amount of stuff in it, and so there's a finite amount of hydrogen that can be fused. So in about 5 billion years, when we run out of hydrogen, what's going to happen to the sun? At this point, the sun will enter an evolutionary stage called the red giant phase. Now, we've all probably heard about red giant stars, but what actually are they? As a star enters the red giant phase of its life, it starts to cool down and expand. The outer atmospheres of the star expand way out. For about 1 billion years, our sun will be a red giant. It will be a star that is really expanded and really cooled down. But although the outer atmospheres are cool, the inner core is still slowly heating up. This slow increase in temperature eventually allows the core of our sun to reach a temperature where it can fuse helium into larger elements. Fusing elements together that are heavier than hydrogen takes more energy, and so you have to reach specific temperatures in order to be able to do that. So for about 100 million years after being a red giant, our sun will do helium fusion in its core. It will still be a giant at this stage, very extended atmosphere, but it will be slightly hotter than it was when it was a red giant. Now, eventually, the sun is going to run out of helium to fuse just like it ran out of hydrogen. As it reaches those stages, it becomes more and more unstable. Convective processes will bring up a lot of stuff from the lower layers of the star's atmosphere, and an increased pressure will start to actually push away the outer layers of the sun. Eventually, all of the sun will get pushed away from the core, leaving behind what we call a white dwarf. The white dwarf is just the very dense, mostly carbon, leftover core of the sun. It's so dense, it's like taking the entire mass of the sun and fitting it into a sphere the size of the Earth. So a white dwarf is really small, but it's very hot. Because it's so hot, it's going to produce a ton of energy that's going to cause the gas that's been pushed away from the sun to glow. And so what we have is a planetary nebula. And planetary nebulas look like these. They are absolutely gorgeous. You have some sort of small white dwarf in the center, and then the glowing outer layers of the sun's atmosphere. So in about 6 billion years, this is what our sun is going to look like. It's going to be gorgeous. But I have some bad news. We're not going to be here to see it. In fact, Earth will probably cease to exist as we know it about 1 billion years before this happens. In about 5 billion years, when the sun becomes a red giant, it's going to expand so much that the outer layers of its atmosphere will actually reach the orbit of Earth. That means that Mercury, Venus, and yes, even Earth are going to get swallowed up by the sun. When our sun becomes a red giant, the solar system will be pretty much entirely unrecognizable. So that means we won't get to see when it becomes a very pretty white dwarf and planetary nebula. To visualize all of these stages of the sun's evolution, astronomers use a tool called the HR diagram. This is simply a plot that has temperature on the x-axis and brightness on the y-axis. Now, something to note is you can also put color on the x-axis because the hotter a star is, the more blue it is, and the cooler a star is, the more red it is. So temperature and color are kind of the same thing. So here is a visualization of all of the different evolutionary stages we just talked about. You can see how the sun is going to move around a lot on this over the course of its lifetime. So there you have it, a slightly more detailed look into stellar evolution. I hope you found this explanation stellar. I'm sorry. I'm sorry.